Hello, everyone. Good afternoon. In our presentation today, we are going to discuss about a CPU and how to overview, troubleshoot its utilization. We will be covering in the contents of this presentation a basic overview, the cluster multiprocessing feature, the single versus multi-threaded processes, the split plane architecture, the HT split, the changes in dashboard and on the CPU reporting in both versions. We will see on version 13 and the new dashboard on version 14. The tools of and what tools do we have to prove CPU usage and how to troubleshooting. And we will cover some resources and known issues. So let's get started with the overview. This presentation will be mainly focused on the Tmm CPU usage. The Tmm run, you will need to know that runs as a real user process within the Big IP operating system. The CPU resources are allocated to both Tmm and host processes. The Tmm is explicitly provisioned to be allocated significant CPU cycles traffic for the processing. One single CPU core systems, like for example the 1500s, the Tmm has priority on CPU usage, but will yield cycles to other processes when it is idle, to the control plane processes. On multiple CPUs on multiple core systems, separate Tmm instances are created for each CPU. So what influences the CPU usage? There are three major things. The number of processes, the processors installed on the Big IP system, if we're talking about a single CPU core system or a multi-CPU multi-core system. The Big IP software version, it will depend on each version, how the CPU or allocated CPU to each process will vary depending on each version. And obviously the license and provisional Big IP models. If we have just a simple box with running LTM, we will see Tmm taking all the majority of the CPU usage. But if we're running models like ASM or AVR that are more process intensive, we will see there the difference. So let's move on with clustered multi-processing. This is a traffic acceleration feature that it was introduced a long time ago on version 9.4.0. This feature allows the Big IP platforms that contain multiple CPUs to run multiple Tmm instances. With multiple Tmm instances simultaneously processing traffic, the system performance is enhanced and traffic management capacity is expanded. So that's the idea of this feature. The CMP feature is automatically enabled on Big IP platforms, ensuring that all instances of Tmm are available to process application traffic. When the CMP is enabled, the system creates what it will do. It will create separate traffic management microkernel or TMMs instances for each CPU to share the workload among all those CPUs. On these solution articles, you can expand on these concepts, on the concept of CMP, depending on the version that you're interested in. So for single versus multi-threaded processes, when we're talking versions prior to 11.3, the Tmm was a single-threaded process. This architecture did not scale well when increased the hardware and network performance. So beginning in Big IP 11.3.0, the Tmm supports a multi-threaded architecture. Under the multi-threaded Tmm model, the basic context of execution becomes a thread. So the big AP system allocates a fixed number of threads per processing core, which may include hyperthread cores. The threads reside in a shared virtual memory space and share a small subset of modules to reduce the greatest causes of overhead. The TMP feature allows platforms that contain multiple CPUs to run in a single TMM process for every CPU and multiple TMM threads per processing core. So then the split plane technology, the HTP splits in software version 11.4 and earlier, each HT technology core processes both data plane, so TMM, and control plane tasks. So split plane technology introduced in 11.5 dedicated separate CPUs for control and data plane tasks. Having TMM share a logical core with control plane task requires the traffic management operating system to perform context switching between TMM and control plane tasks. This context switching introduces latency that can impact performance. Additionally, the control plane and TMM tasks may block each other. For example, if we have a long-lived control plane task running, this control plane task running may block the TMM and prevent it for servicing data plane and packet processing tasks. Similarly, if we have a busy TMM, this busy TMM may impede or prevent completion of control plane tasks, such as management. Let's say if access to the GUI, etc. So starting in 11.5.0, the data and control plane tasks use separate logical cores on system with hyperthread technology CPUs. These new split planes behavior improve the performance by dedicating and prioritizing resources for TMM. Meanwhile, all other processes can still perform control plane tasks that are non TMM related, even while TMM is fully utilized. Each hyperthread technology physical core has a single TMM running. So the even number hyperthreads, the 0, 2, 4, etc., are dedicated to TMM as a high priority process to service data plane tasks. And the odd number hyperthreads cores, the 1 through 1, 3, 5, etc., process control plane tasks at a normal priority level. However, if the TMM at some point reaches 80% utilization, the odd number hyperthread throttles control plane tasks so they can use only 20%, allowing it will allow the TMM to use the remaining resources. So when this happens, the big AP system logs a message in the kernel log that we will see in the next slide. You're gonna expand on this information on this Troubleshooting article that you have there. So when this happens, if the TMM reaches 80% and needs more CPU to process data, it will throttle on the odd core, and this is what it will be locked on the kernel log. So you can see that the idle enforcer will be triggered, and you can see here that it will be triggered on the odd cores. Here you can see example on core 1, 17, 3, 15, 7, and 5. So when the idle enforcer is active, the top will when you run a top command, you will see that CPU utilization of the odd number CPU cores is increasing. You will see a high CPU on those odd cores. So here we can see a visual example of when we have the hyperthread technology split off and on. On the logical core, we have two instances of TMM, but they're sharing the control plane. Processes. When the HTTP split is on, the logical core, one of the logical core will be assigned to purely process TMM, and the odd core will be handling the control plane tasks. Note that when HTTP is on, the odd number core is partially halted. When this throttling occurs, increasing TMM access across all physical system cores. The benefits of the HT split is better TMM memory management, as there are fewer threads, half the number. And so the configuration objects are processed by fewer TMM, for fewer TMMs, thus saving memory used by TMM. We will have efficient scheduling. TMM will not be scheduled from CPU by control plane tasks. If we have a long-lived control plane task, the TMM will always be guaranteed to have what it needs to run the data, to process the data. And to better control plane responsiveness on system under load. So let's say that we have web UI access timeouts and large configs loading time are reduced and have less impact when we have the HT split on, because we have the control plane tasks, a percentage of that core assigned just to handle these type of processes. So this would be, it's just to show an example of a case of a study when on the kernel log, we noticed that the idle enforced was triggered. So something happened. This might have think that something happened at some point that TMM now is requiring more resources. So we noticed that the accelerated increase in the kernel log message, like the following. And the change, it was the ECD Diffie-Hellman base cipher suite. So what is the meaning of this message? You can find explanation in these solution articles. So basically, the SSL algorithms that are hardware accelerated, like this one, this particular one, ECDHE, is no longer handled by the Nitrox card, and is now processed by software. Since now it's processed by software, we will see higher CPU utilization is to be expected with this change of behavior, and this explains why now we can see on the kernel log that the idle enforcer is triggered. Okay, we will discuss now the changes in dashboard CPU reporting. So with the introduction of HT split, the dashboard has been reworked. The average CPU is an aggregated of the data plane, TMMs only. This means that the control plane CPUs are ignored. The highest and lowest CPU can still be one of the CPUs, control or data plane. We will see now that in an example. The system CPU calculation is now done differently, and two sets of values are computed. The average overall TMM data plane CPU and average overall CPUs except the last one. And the higher CPU of the two sets of value above is presented, it will be presented as the overall system CPU usage. The reason why here the average overall CPUs except the last one is because AVR processes and some ASM processes are pinned to the last one, to the last odd core. So here we can see an example of the top output compared side by side with the dashboard output. Here on the dashboard, you can see that the PC CPU is 100%, which could be alarming when you are just reviewing the dashboard. By getting a detailed detailed look on the top command, you can see that we have the cores here, 3 and 5. That those will be control plane cores that are the ones running at 99%. So we can see here that TMM is actually not affected. There is a control plane processes and that is taking all the CPU on those particular cores. So basically, you can get alarm by check the dashboard, and when you compare that again against the top, you can see that the data plane Tmm CPU usage is relatively small. You can see here that as well on the dashboard that it reports an average of 50%. But we have I have to take in mind that we have the PC CPU is spec at 100. So the average CPU appears to be calculated as the average of the control plane values divided by the number of control plane tasks. So even this average of 50% is not a good indication if the system CPU is overutilized or running high. Okay, now interpreting the QQview CPU graph. Here we have an example that's a graph that we can get on the highest number, on the QQview. And here you can check how the CPU utilization can be observed on the highest number core, would be core 7. In this point, there are two solution articles that you can bear in mind that could cause this behavior. As I mentioned previously, there are ASM processes and AVR processes that are now pinned to the last control plane core. We can take a look to one of these articles. Can bear with me for a second and I will show you. Okay, this is one. It will be important for you to have in mind if the unit in question is running ASM. There is an obfuscation process that runs and could, it is expected to see an increase in CPU, and it runs every 24 hours for about 2 to 4 hours. So you can see the odd cores every 24 hours increasing in utilization. And the other one will be, let's get back to the presentation. This is the other example. We can see here that core 11, we can see spikes every now and then, every 5 minutes, that there are attributes to the AVR. So for this particular behavior, we have that this is expected as well, because the BigAP now aggregates all statistics that it will correspond to AVR every 5 minutes and include all statistics. And since this happened on the latest odd control plane core, it will not affect traffic. So which tools do we have to testing and troubleshoot CPU utilization? Basically, there's a combination of a bunch. One is top and TMSH command. In some cases, you can use also strace command. It can be applied with diagnosing CPU utilization issues. There's also this solution article is very useful to understand how to interpret how the top command works. And the other thing that you can do, or we will cover this on a example later, is to script these top or straight commands. So you can run it periodically, so you can have a picture of how was the CPU utilization of certain time. And the other thing will be the analysis of the graphs in the QK view. So when you are on the QK view, ordering the top columns by CPU processes could help you to illustrate a data plane pinned to even number cores and control plane processes pinned to odd number cores. And here we go in a little bit more in detail of the tools that you can use. On the GUI, if you're working directly on the particular units, you can go to statistics, an overview, performance, system, all system CPU usage, and then click on the detail graph. Let's take a look. So we have here our units. And we will go to statistics, performance. Here on system CPU, we will have an overall of the system CPU usage of the entire system. It doesn't take account in account all the cores and data plane and control plane. So what we like to do is to review the detail graph. So in this one, we can see how the control plane and analysis plane are the ones running a little bit high in this particular example. We can see here the last 3 hours by core. So if we check what it will be TMM cores, CPU 0, CPU 2, and CPU 4 and 6, they are running low, but we have the odd cores running a little bit high. So we would like to review why this is happening. Let's take a look with more, expand to more days. Here, this is short, but we can see that it's happening each day on the odd cores. We have this high utilization on CPU. If we check the last 24 hours, so here we can see that is a recurring behavior from 6 a.m. The other day, it will start again at this increase in CPU. So from the graph, we can see that something is going on the control plane cores. Then we can take a deeper look of what's going on. Let's open and connect to the console and run some tmsh commands. The first one will be tmsh show sys CPU. And basically here we have an output base of it is user plane nice or system or where it's at, if the core is idle per core. But actually we don't know which process is actually causing the high CPU. We can review the tmsh show this tmm info. this will help us just to review if we have an issue with high CPU on TMM. We can review what is the usage on based on radio, percentage of 5 seconds, 1 minute, or 5 minutes for a particular core that is handling TMM. And the other useful, let's go first and check the QK view, the iHealth. So this is a QK view generated for that particular unit. Let's generate a new one. So we can take a look and how to troubleshoot quickly on the iHealth and what to look for. In the meantime, while this is running, we can run here a tab command. So we know that right now we have the odd cores running a little bit high. So with this tab command, we can see here that Java and well, right now QKView is taking CPU, but Java is most likely the one taking the CPU, but we don't know exactly in which core. So what we recommend to do is to modify the top output as follows. So once you run the tab command, login, you need to be logging as root to run the tab command and press 1. So you can see all the CPUs. Now you can see all the cores and how they're being utilizated separately. Then we can press capital S to add the short-lived child processes account, and F to add some columns, and that it will help us. With J, we will see the last CPU used, and B, check the parent ID, to check the process ID. So then we can just save with W. This will be our top outputs from now on. And here we have a better idea of what's going on. We can see now that is the process Java that is consuming a lot of CPU is running on core 5, one of the control planes ones. And we have ASM as well running on core 3. And another one, the ASM cron D running on 7. So these could be the ones that are causing this behavior. Let's go back to QKView and downloads, and we will import that, extract that on iHealth. Let's change the name quickly. And we can upload it now. wait for it to extract it. And in the meantime, we can cover how to script if we want to monitor and take a top command in a specific interval, so we can have a picture of the CPU utilization. So what we can do is to create a script on shared temp. Let's collect debug sh, and we will use this as a script. So basically, what it will do is run 5 times. Every time it runs, it will wait for 300 seconds, and it will collect and store the output of the top command and tmctl. This script will be particularly useful on units running software version prior to 12. Because starting on version 12, we have the tmstat snapshots that they are automatically generated that we can go and check even with a QKView. We will go, we will review now those in a second. So now we will just to make that file executable. And now we can simply run the file. And this will start running the top commands in tmctl. It will collect us for us and save that into a file. Let's duplicate here. We can check the output. So here you can see how it's starting to collect the top command. And the same for tmctl. Okay, so let's go back now. I think it should be ready, and open our QKView on iHealth. So the first thing to check when we're troubleshooting CPU usage issues, go to graphs. To get a general idea of what is the behavior. And here we can see the same. Something is happening on the out course. Let's take a look one day. So you can see that. Okay, so we can go now, and if with the commands that are available on the QKView, if you use top command here, you will have just a picture of how it was at the time that QKView was generated. So if the CPU was not high at the moment, you will not get an exact idea of what's going on. Like here, we can see just TMM, but we don't know what's going on with on the out course exactly. And nothing seems relatively high here. So here you can use the tmctl. Go to tmctl-a blade. So here we have a bunch of statistics that are collected that we can review. We have this CPU info stats. It will just give us a general idea. But the one that is interesting to check is this one, the proc PID stat. That is a table that it will give us the CPU utilization per process, per core. So here we have an idea there. At the moment this was generated, which is the process taking the most CPU. You can see Java here. This is one way to do it using the QKView. But if you want to have more data, because this is just a particular snapshot, you can go, if you extract the QKView on your machine, or if you have access to the machine, you can go to this path. It is where the TM stats snapshots are stored. So go to CD share, TM stats, snapshots, blade 0 public. And here you can select the intervals. This is in seconds. We will use now this one. And here you can see all the TM stat snapshots that were generated. It will generate one each day here. So we can review the one from today and yesterday. So to do this, we will use the tmctl command. That file to open the file. So 1022 first. And what we like to check is the same as we did now on the QKView, will be the proc PID stat. So here, this is the table that we want to check on that particular file. And here we are just filtering for what we're interested. The process name, the processor, the CPU usage, and the recent CPU usage. And at the end, we're just sorting and getting the top 10. The top 10 processes and then CPU usage. So here we have the TMM. Let's go and check new snapshots from the 23. And here we can see TMM is also at the top, but we have a start, ASM start. We can go now and change, instead of using this interval, we will use the need to check the file. Select the last one, 05. So you can see here, we have per hour in these snapshots. And we'll run again to get the proc PID stats. And here we got it. We can see that it's Java that's consuming a higher CPU. So this will match what we discussed in this solution article. Since ASM is enabled, we can just confirm. So we will check the resource provisioning. We have ASM enabled in AVR. So if this is Java what is running, it will be actually the obfuscation job for the JavaScript that the Big IP ASM and Big IP's FDS system used to protect against reverse engineering. So that's why we can see this odd cores going high every day, every 24 hours, and it will take around 2 to 4 hours while this process is running. And due to HTTP split, this will not affect traffic because TMM is not being the TMM processors. The processors that are assigned to TMM are not affected by this. Okay, so let's go back. And well, the other commands that obviously you can use or run is the PS command. So just to confirm, once you have the ID or the process, confirm what is running there. To confirm the ID of the process. Let's do an overview of what the dashboard on different versions. So this unit is running version 12.1.2. So let's go to statistics dashboard. And this version of dashboard on versions prior to 14 are based on Flash, and starting from 14 is based on HTML5. So it will be a better increase in performance and easier to use. So you will see now in a second. So let's wait this to populate. Let me try to reduce this a little. Okay. So here we can see CPU usage, but it is, we have to bear in mind that it's the busy CPU is running at 64. It could be alarming if you don't know that we're actually talking about HT split, and this could be one of the odd cores that is running at this level. So one way to check per core will be here to have a better idea and not to rely just on that particular dashboard. We can see here how exactly the odd cores are the one running high. Now let's review the same but on version 14. It will be this unit. And let's go and check the dashboard. see how this one is faster, and it have a different information. It's better if you want to create your own dashboard. It will be easier with the one on version 14. And here is, you can see that the information, I believe it's better information if you can see that this is, it is showing the CPU, but the control plane CPU, not the PC CPU like in the other version. And also you have the same, the last minute graph here. So let's go back to our presentation. Oh, one thing that I don't want to miss, just to see here. Let's go to check the statistics here quickly. Performance, CPU, have to go to the detail graph. And this is every 3 hours. Where we have our QKView. Let's check it here. So here we can see that there is a spike on core 7. Let's to have a better idea on one day. Let's see if with 3 hours we can see it. Yes, here we can see the spike. That it will be the one that I mentioned, AVR. Sometimes it could be higher, it depends of the the amount of data, statistical data you have in processed. So you will see this spike every 5 minutes. Okay, if we go back to our presentation, the resources and known issues, here you have a list of solution articles and known issues that you need to be aware of. And the others that it will be useful, like the one understanding that the top output. And we can briefly, the summary of what we discussed so far. So even though the CPU resources are allocated to both TMM and Linux host tasks, the significant amount of resources will always be allocated to TMM. Most important thing is to handle the traffic, handle the data. A combination of the dashboard, live top output, and QKView graph and TMSH command are the first steps, as we did just now, to interpret and ultimately troubleshoot the CPU usage. And I will add here the TMCTL if you are running on software version 12 and above. You can use the TM stats to review quickly per hour or per day the usage of CPU per process, per core. This is just, this will be the list of tools, utilities that you can use to troubleshoot the CPU utilization. As we discussed, top PS, TMSH shows sys proc info. If we're looking, if we want to troubleshoot and we know that we can see high CPU on a TMM core, we will need to rely on these commands, on TMSH shows sys proc info or TMSH shows sys CPU. Also, you can use the proc CPU info, the QKView, as we did right now. Basically, just check, review the graphs on different intervals to confirm what's going on. You can go to the commands part of the QKView, run top and run tmctl from there. Also that you will be limited on the QKView because you can see only one of the snapshots, the last one. And the tmctl utility that we discussed. You have these available. You can run it on the live unit, or even if a customer just generate a QKView, you can get the QKView, extract the QKView on your unit, and just go to that path. The share tmstat snapshot played public, and from there run the commands to get what you're interested in. In the context of opening a case while troubleshooting CPU utilization, what is helpful is to have a timeline for when it was noticed. So it will be good to have a baseline of when it happened, when it got started to see this issue. If higher CPU utilization was noticed post upgrades, that is a timeline. We cannot see that we were on 11.6.4, we upgrade to version 13, and now we can see a high CPU. So to aid with troubleshooting, it is helpful to take QKViews over sample periods of time to compare graph on behavior. This will aim if you are on previous version, pure version 12. Because as I mentioned, starting on version 12, we have the tmstat snapshots that we can see the whole history of what's going on different statistics. The HT splits and CMP technologies are key to understand how TMM and the host process CPU is allocated. The data plane are pinned to even number CPU cores, while control plane tasks are pinned to the on number cores. Remember that for AVR and ASM, some ASM processes are pinned to the highest number core. And the control plane cores are excluded for computation of the CPU utilization. Well, thank you. That will be it for today.